thing is funded by NBHM and so on. So I was kind of what should I say, conservative in how many of these things of notes I printed out. So if some of you haven't got these notes, I just want to tell you that you can access all the notes that I put out here. They're all available. See, there's a home page, there's a website for this workshop. If you go to that website, you will see all these notes that I put up there. So if you want, you can download it from there and look at it. And anything else I need to say? I can't think of anything, so we'll start. And so I repeat what I said during Panto's lecture. If any of you find the going a little fast or whatever, please feel free to immediately stop me and ask me why I put on whatever I have put on. And so let me first also point out that you would have received various sets of notes in the packet. Of those, I am responsible for my set of courses. For Partho's set of courses, he is given one set of notes on C-star algebras. For actually, if you see the home page, you will realize which is for me and which is for Vijay. And which is for Partho. The point is that for my lectures, not only are there the set of lecture notes that I have handed out, I've also handed out a few small sections from 3 different books that we find it convenient to refer to rather than writing everything down in these notes. So without further ado, let's get started. So as you see, as you must have noticed, the topic of my course of lectures is orthonormal algebra. So you will be seeing sooner or later that unlike C-star algebra, which is what Partho is going to talk about, which are defined, which are just algebras with a star with an involution, with an adjoint, and which have a norm where there is a Banach spaces, Banach algebras, with some properties. And so the theory is somewhat less complicated than these can be. The reason being, these algebras are they also have an element of point set topology, general topology. So what is inherent in the structure of the algebras is a certain topology. I'm getting ahead of myself, and maybe this thing will be clear as I go along. So let me start with some very baby topological statements. Partho mentioned in his lecture something about a net, and he talked about convergence of some net. So does everybody here know what a net is? Please raise your hand if you do not know what a net is. Don't feel bashful. I want to see those hands. So let me start by addressing this question. See, the point is that when you start studying metric spaces, you find that all the notion of a set being closed continuity of functions. Most of analysis that you learn in college or BSc or whatever, which deal with the real line or more generally with metric spaces, you're interested with sets being closed or compact, and you're interested with functions being continuous. And these are usually addressed using sequences. So for example, that a set is closed, A is closed if and only if whenever you have a sequence A and an A which converges to a point, and all the members of the sequence come from A, this implies that A is an A. That is, closed sets are those which are closed under the formation and process of taking limits of points in that set. And similarly, a function is continuous precisely when it preserves convergent sequences. Okay? F of limit xn equals limit fxn. In order to verify the sets of closed or functions are continuous, it is convenient very often to work with sequences. Now, the point is that when you go to more abstract topological spaces than metric spaces, unfortunately, this is no longer true. When you discuss abstract topological spaces, it may be the case that there will be no sequence which converges except sequences which are essentially eventually constant. So here's an exercise for you. For example, if you take any set X and you define a topology by saying that the open sets are either the empty set or complements of countable sets, then you prove that no countable. No, I want co-countable. So if you take this co-countable topology, then you can verify that this is a topology, and you can also verify that if you take a set, the only sequences which converge in this topology are the sequences which are essentially eventually constant. So, for example, knowing something about when sequences converge is not enough to determine when sets are closed. So, one needs to get away from this notion of sequences when studying abstract topological spaces. And the substitute for sequences is played by the notion of nets. Nets are kind of generalizations of sequences. So, what are they? So, I don't want to go into details here, but I will just say that, so I will just use a different symbol then. I won't write n, I will write of alpha to indicate that the index set is some kind of more general than a set of integers, and that set will have a certain natural order, and so the good properties which make all your arguments true are what are that the index set is what is called a directed set. The argument that you use very often is that if something is true for everything beyond a certain state, something else is true for everything beyond some other state, then if you go far enough beyond those two stages, then both those desirable properties will hold. So that is one of the requirements of a directed set. So a directed set, we can go into this in the problem session today. So let me just say that there is a notion of nets rather than sequences, where all these things will be true when represented by alpha. A set in a topological space will be closed if and only if, whenever you have a net of points in that, so you just replace the word sequence by net. You have to be more general in your, more admissive in the collection of sequence-like objects that you consider. Okay, so I will use this, and you will see this, the usefulness of this notion when we verify that some sets are closed or some sets are, some functions are continuous, which you will need. So let me go ahead. So the reason is, so I will use this notation B of H, or this will be the collection of all bounded operators on a Hilbert space. So password I have already observed for you that there is a natural norm on this which makes it a Banach space, namely the operator norm and so on. But what is relevant in the study of orthonormal algebra is certain other topologies. Namely, there are certain other topologies on the space of operators that I wanted to introduce. To introduce them, I start by saying, in general, if you have a Banach space, for example, then there is a notion of strong convergence, strong topology. There is a strong topology and a weak topology. Strong is the norm topology. Something, a net, I would say, a net for the norm thing, you don't have to talk about nets, it's enough to look at sequences. But when the underlying topology is sufficiently nice, sequences surface. So in general, one says that X alpha converges to X strongly. This means that norm X alpha minus X goes to 0. And weakly means that you would have already seen the use of the word adjective weak in the password later. Something happens when you apply continuous functionals to it, then you say that thing happens. So see, the net converges weakly if when you apply any continuous data functional, you have this convergence. Already this weak topology is one where you actually need nets. It is not enough to deal with sequences in general. Okay. So for us now, in B of H, there are analogs of this, which are the so-called strong operator topology. I will use this abbreviation. And the analog of the weak operator topology, which are defined by saying that if I have a net, now the elements of my space are operators. So a net of operators will converge to an operator T if, so actually let me do a reversal already. I don't want to use the symbol. Okay, I'll go through this and then tell you where I'm saying it. So this happens strongly if for all x in the underlying Hilbert space, T alpha x converges to Tx strongly. The connection of operators converge in the strong operator topology. For every vector, when you apply the operator, they converge in the strong sense. And they converge in the weak operator topology if this happens to be. So what is the boundary area functions on a Hilbert space? They come by taking inner product against something. So this is almost saying that okay. So now let me go back to the little noise of word make. I want to change notations. It is a habit really. That usually you use symbol x here for vectors because you work in a vector space, and the vectors are what is important. But when we work with operator algebras, it is those operators which are the elements of interest. So I will use these small letters, which are the ones one uses most often, symbols like x and little x and y and so on, for operators. That is for elements of these algebras of operators. And so typically the way I would say this is that x alpha net of operators converges to x. So T will not be norm of x alpha xi minus xi converges to 0 for all xi. So the convention is that Greek letters are vectors in Hilbert space and Roman letters are operators. And similarly, weak operator topology so here we're talking about applying against, so I want x alpha xi to converge to x xi for all xi in the weak sense. So what does that mean? Because the functionals come by taking enough products against vectors. This amount demanding that x alpha xi converges to x xi eta for all xi in eta. So what will be important for us are this strong operator topology and then the weak operator topology. There will be more topologies coming up, but we'll come to them as and when we have to. Okay. So let me start with one little lemma which will already show you the importance of. Okay. So here's the problem. See, we'll be interested in knowing that some set collections of operators are closed in some strong operator topology or weak operator topology or whatever. So we'll have to verify that if I have x alpha converging to x and if x alpha comes from xn, then so does the limit. So which means we have to verify for every xi or for every xi and eta that something happens. So the content of the first proposition is that you don't have to really verify for all xi and for all eta. It is enough to verify for enough xi and eta in some sense, provided the collection of operators have some satisfy reasonable conditions. So what is the proposition? If you have a collection of operators which are uniformly bounded in norm, so on uniformly bounded sets, so it says that x alpha converges. So I want to verify weak convergence, for example. And so say that x alpha converges to x strong operator topology is equivalent to saying that for all xi in some collection S, which may not be the whole Hilbert space, where S is total. By total, I mean that the linear subspace span is dense. So, for example, for S I can take an orthonormal basis. So that is the total set. So if I have a norm-bounded family of operators, in order for me to verify that they converge from the strong operator topology, it is enough to verify on just orthonormal elements on that basis. You don't have to go for everything. There is just a simple observation, but very useful. We use this very often. And similarly for weak operator topology. Then I have this thing for all xi eta. I'm not spelling it out, it's written in the notes. So in order to check strong or weak convergence, it is enough to verify these conditions. So let us look at some examples now of this. So first, I want to spend the initial some amount of time discussing some kind of subtleties. See, when you study topological groups, for example, you have a group with a topology, and you have a group with your multiplicative structure, and you want the multiplicative structure to be compatible with the topology. Okay? But you will find that there are problems with various of these operations, like taking adjoints, taking products and so on, when you look at these other topologies. So there are some certainties that you have to vary of. So this is what the first, starting on page 3, this is what is the example 1.2 makes various noises like this. So let me just highlight some of those points here. So one of the, at least philosophically, one of the differences between weak and strong is the following thing. Usually, if you take the unit sphere in a balance space, that will always be closed. If you have a collection of unit vectors which converge, then the limit is going to be unit vector. However, if you talk about weak convergence, you can have unit vectors which converge weakly to 0. The typical example is if you take an orthonormal sequence in a Hilbert space, they are all unit vectors, but they will nevertheless converge weakly to 0. So this is typically the kind of thing that will happen in the weak operator topology. You may have, so let me just say this. What is the first example? So I'm just talking about the example. That is that you can have isometry with a unit vector which converge weakly, but the limit may not be an isometry, maybe 0. So for example, as evidenced by the example of an orthonormal sequence in Hilbert space, that is a typical kind of, the typical manifestation of infinity in infinite dimensional spaces is something like the unilateral shift. You have this isometry which is not onto. It is one-to-one but not invertible. Right? It is not preserving but it is not onto. And this shift is kind of symptomatic of many of the things that happen. So, for example, if U is the unilateral shift. So, by which I mean that this has natural basis xi n, and this sends xi n to xi n plus 1. This has a basis n greater than or equal to 0. So that is why it is called a unilateral, because the index set is taken one side, going from 0 onwards. Whereas if we are taking a bilateral sequence, if the basis that has been indexed by the integers, all integers, then n going to n plus 1 is one-to-one on 2. That will be a unitary operator. But if you only take the positively indexed L2, then it is going to be an isometry. But it is not going to be onto because the range is going to miss out the 0th way. Okay, if you take this U, then you can see that every U to the n is an isometry. And U to the n converges to 0. Weak. So let me apply, rigorously convince you of this, applying the previous proposition that I wrote down. To verify this, I need to take it on a total say, on an orthonormal basis. So if we take the standard basis, what does U to the n do to the standard basis? It just shifts that basis out. And that is also an orthonormal set which is clearly converging weakly to 0. So U to the n converges weakly to 0. And it should be clear that in fact on B of L2, if you look at the adjoint mapping, x going to x star, that mapping is clearly continuous with respect to the weak operator topology. Because weak operator topology convergence was the requirement that then those inner products should converge. But you can, to say that, you understand what I'm saying? X alpha converges to X means that X alpha xi eta converges to X xi eta. That is the same as saying that xi X alpha star eta converges to xi X star eta, which says really that X alpha star converges to weakly to X star B. So the adjoint operation is trivially weak operator topology continues. Okay. So as a result of this implies that also use to the n star converges to 0 weak operator topology. But this is really nothing but U star here. U to the n converges to 0, U star to the n converges to 0. But what about U star to the n, U to the n? This is the identity. U star to the n will push it forward n times. So U to the n will push it forward n times. U star to the n will bring it back. So U star to the n times U to the n. U to the n is the identity. Right. And clearly, so this means that multiplication is not continuous, jointly continuous. U to the n converges to 0, U star to the n converges to 0, the product does not converge to 0. The product is always 1. So multiplication need not be in fact, one of the remarks, the last point in this exercise shows that this is also true for the strong operator topology. You have to work a little harder. That exercise demonstrates quite a spectacular failure of this continuity. Namely, if you take a collection of operators which satisfy x squared equals 0, then that last part of that this example demonstrates that collection of important operators of order 2 x squared equals 0, those things are strongly dense in V of A. Any operator strongly approximable by elements whose square is 0. So clearly, by the same kind of reasoning, it should follow that it is multiplication is not jointly contained the strong operator. However, I mean, not everything is hopeless. There are good things that happen in spite of this initial evidence of bad things happening. The crucial thing is that on non-bounded states, typically, for example, so if for any Banach space, one will write x sub 1 for the unit ball of x. All operators norm less than or equal to 1. So on a set like BH1 or any multiple of that which is BH sub n, on such things, in fact multiplication is jointly even strongly continuous. That's what I was saying. In any Banach space X, I will write x1 for the unit ball of x. All elements of x with norm less than or equal to 1. BH1 is all operators of norm less than or equal to 1. Okay, this is also we can maybe discuss this in the in the tutorial today. There's an easy application of that lemma that I said. To do this, it is enough. So I I've never not been involved over this kind of thing on the spot. So we will see that multiplication is indeed jointly strongly SOT continuous. If alpha converges to X and Y alpha converges to Y. And by the way, I keep talking about converges to X and converges to Y. Like in a norm space, you don't say that something is continuous. You don't have to keep saying that if Xn converges to X, then Fxn converges to Fx. If you're talking about linear mappings, you can always assume the limit is 0. So to say that this kind of thing is jointly contained, you can always assume that the limit is 0. If X alpha converges to 0, Y alpha converges to 0, then X alpha Y alpha converges to 0. That is what this statement means. So you can see that it is enough to see that. And okay, please never spend more time on this. So now we get to the there are some notations. I will write so with my notation convention of what I wrote was correct. It's just the straight test is for operators of inverse space, and I write script test for operators of subsets of inverse space. Okay, and I will write this will denote the linear space spanned by. So span S over is the linear span of X. But since we are interested in topological considerations, I will also introduce this other thing. I will write S for that way where going to be easier one. What span is closure in the norm closure. Span S is a subset of Hilbert space. So by box this, I will mean the closed subspace spanned by S. And this will be similarly closure of span S
span of script S.
Sorry? Yeah, this is a script S. Thanks. But when I'm talking about operators, now I have to be careful about whether I mean strong or weak operator quality. Now this is one of the pleasant facts. So there are many statements that I will make without proving, and so that is why some of these things have been given, where all these details have been worked out. There is appropriate sections of this book by Satila and Jizo, which shows the following very useful and important fact. That in fact, if you take B of H, and if you look at linear functions on B of H, let me assume it. Then, in fact, F is, I don't even have to say norm, this means norm continuous. So, if I take a linear functional on B of H, I want to say that, it is F mapping BH linear. F with SOT continuous. WOT. The details of this proof are also about. Actually, this is very, very well written with all these kind of nitty-gritty facts first out. It is not by Satil and Sido. You will find facts like this proved over there. So I urge you to look at those things carefully. Okay, well, so one consequence of this fact is that whenever you have, see, these things are what are called locally convex topological vector space. B of H with either of these topologies is an example of a vector space with a topology given by a family of semi-norms. And I've defined the semi-norms in the notes. I don't want to go into that now. But it is a fact that when you have such locally convex topological vector spaces, it is a version of the Hahn-Banach theorem for these topological vector spaces, which says that in fact, if you take a convex set, to say it is closed in the strong topology and that is closed in the weak topology are the same. So the things which are continuous with convex sets, which are close to the assert let me repeat that. The statement being alluded to is that if for good locally convex topological vector spaces, you don't have to understand all these words. The B of H with either strong or weak operator topologies are examples of this. So if you take such a thing, then to say that and see the convex set. Then C is strongly closed. So here, when you have got strong refers to the topology of X. So X came with the topology. It is a vector space with the topology given by semi-norms. So it is strong with respect, it is closed to that topology. If and only if it is weakly closed. Then, what do I make by the weak topology on such a locally convex vector space? You take it is the smallest topology, so you take all the linear functionals on X which are continuous with respect to the given topology, and you may put the smallest topology on X, which makes all of those continuous linear functionals continuous. So that is the weak topology. So, to put it in a nutshell, what is the point is that being for a convex set to be closed is a property that is dictated by what linear functions do on it. That's what philosophically this trying to tell me. And so, if I know that two different locally convex topologies on some space have the same linear functions, then it is said that they have the same closed convex. So in particular, if we take a linear space, then it's certainly convex. Vector subspaces of B of H are WOT closed precisely when they are SOT closed. And we better more in convex set which are intersection with maybe balls or something. So to say that something is so this is slightly more general than what I want here. So now let me get to slowly we're inching our way towards orthonormal. One more bit of notation. So in particular, probably if I define S as maybe small s, I keep getting confused by my own notation. We take collection of operators, then these two things are the same. Doesn't matter which topology you take. So when I want to take the closed subspace generated by some collection of operators, then it doesn't matter whether it takes which of each of these operators. So one more definition that we need. Given S, I define this prime is all the elements in A of H which commutes with everything in S. I'm sorry, my handwriting is normally bad, pen is making it worse. So, it makes sense as a coding because it is all those operators explained by commute every X in S. That is the so-called commutant of X. So one can immediately make some simple-minded observations about this operation of taking the commutant of collection of operators, which is the following. So let me just read this. The published these notes. So if you have those notes, I don't have to write it down. I don't have to scribble also. So the first thing is that this is inverse monotone, this operation of taking commutants. If you take a larger collection of operators, the commutant is smaller.
What is the item number?
The exercise 1.6. S contained in T implies T prime contained in S prime. Because to belong to T prime, you have to commute with more prime, so it is harder. Okay? And maybe this and more than, and what one can see that so I want to say that S prime equals S. So I will just do a bunch of primes to me and keep in commutants of commutants of commutants. So observe the following thing. There is because clearly S prime contained in S double prime is here. Is double prime. Why? Because to say you are so which implication is the obvious one. If something is an S prime, if something is an S triple prime, then by definition it commutes with everything in S double prime. But clearly things in S prime commute with everything in S double prime by definition of S double prime. So if you are in S prime, then you compute with everybody in S prime, and so it's certainly the prime of that. So S prime is certainly contained in the double prime of S prime. S prime is contained in S double prime. So conversely, that comes by the reverse thing I want to say. Yeah, no, sorry, I should observe that should observe this first. See, S. I should observe this. This is what I just observed. S is clearly contained in S double prime. Because S commutes by definition, everything in S prime commutes with S. So S is certainly contained in the commutant of S prime, so it is in S double prime. So this is true for any S. In particular, it is true for S prime, which means that this is true. On the other hand, by the reversing property of taking commutants, this implies the other thing also. This is actually a triviality. This is true for everything, so this is true. And by applying the reversing trick, this implies the other inclusion. So always S prime is equal to S triple prime. So one sees that, see, if we start with an S, we take it S prime, take it S double prime, S triple prime, and so on. 4 times, 6 times, 5 times. See, these are all equal. Except here, a priori, what is only clear is that you are containing. Okay. Okay, so this is the natural question is, what can you have there? So for this, you should observe that always any prime, by definition, is also written here, so I will just try to observe this. Any S prime is always a WOT closed subalgebra of V of H which contains 1. Actually, I should have said that one of the remarks in the earlier thing is that multiplication is separately continuous. I made a fuss about joint continuity of multiplication. If X alpha converges to if X alpha converges to Y alpha in any of these topologies, then X alpha Y equal converges to X Y, and similarly the other way. So multiplication is always separately continuous. That is no problem, it follows easily from the definition. So I urge you to go back and really convince yourself of all these statements that are being made. So any prime is always what? Is always an algebra. It is always SOT or WOT closed. It always contains 1. So any prime is an algebra which is appropriately closed. And the one other thing you have to observe, so in general, when S equals S double prime is kind of a hard question, I guess. I haven't really thought about the general situation. But mainly because I've been so what are Orthonormal algebras? They are, so I've said that any prime is a weakly closed algebra, unital algebra. A Orthonormal algebra is a thing which satisfies this, but in addition it is self-adjoint because it is closed and taking adjoints. So that is the fundamental double comic concept in Orthonormal. So what I've said as a density theorem. So, in fact, so one I was so say that suppose you have a connection M on contain GOV. And M star algebra. It is a subalgebra which is closed when you are taking adjoints. Then he says that the following are equivalent. So for those of you who are not familiar with this abbreviation, mathematicians use it all the time to denote the following are equivalent. Okay, so if you have a star algebra, then this property of being this double comitron and so what you must immediately notice is this quite remarkable fact that this statement makes. It says that here are these two conditions. You can see my finger. The first two conditions. The first two conditions are purely topological in nature. It is saying that it is closed in some topology. Whereas the third statement is a purely algebraic statement. Something M equals M double prime. So the equivalence of a purely topological requirement on a collection of objects and a purely algebraic condition of that object, you will surely expect that this has strong consequences. That things with this property have something automatically going for them. There's something very nice about these things, and so we will. So I want to try and prove this. So I want to head towards showing this double comitron here. And I ask you to observe a trivial observation and note. If S is star closed, when I write the star of a collection of operators, I mean the collection of stars of elements in that operator. That place. You understand what I mean by the tongue twister, right? It is a collection of all x star for x and s. So if you take a self-adjoint collection of set of operators, then the comitron is also its own adjoint. That is clear. If x and y commute precisely when x star and y star commute. Well, that's what I learned. So a little level. closed subspace. Then you should know that given any closed subspace of Hilbert space, there is an orthogonal projection onto the subspace, which can be associated with a P equal to projection onto each knot. So this is the property of an operator being an orthogonal projection onto a closed subspace is something that can be captured purely abstractly without reference to any Hilbert space. It is just the statement that P equals P squared equals P star. So what I'm trying to say is that if any orthogonal projection is self-adjoint and it is idempotent. And conversely, I'm saying if you take any operator with these two properties, it will be the orthogonal projection onto some subspace. Okay. So I haven't stated the lemma yet. I'm just playing some preliminary noises here. Okay, the lemma says the following: that so let me call this P prime. I call P prime the projection onto each knot. So it will be, and any projection is characterized by this requirement of being considered. So but I want to use prime for reasons that will soon be clear. So each knot is invariant subspace. For each example, every operator in M leaves the subspace H not invariant. That is the first requirement. And so this requirement is exactly equivalent to saying that P prime that is the reason for my introducing primes. I like to keep writing primes to keep track of which is the algebra, which is the Fermi transform. Actually, maybe there is a good point to make the following digression. We'll need this later. See, in general, if you have a direct sum decomposition, if H is H1 direct sum H2, orthogonal direct sum. Or equivalent, if I have any subspace H0, I can write H as the direct sum of H0 and its orthogonal complement. So given any such thing, any operator in V of H can be identified with matrices Tij, with Tij, the bounded operator from Hj to Hi.
What is the M here that starts closed subalgebra of Dh? H naught is invariant subspace for each x block.
Yes, sorry. The star algebra. Sorry?
Can you say the statement here?
Okay. So it's not an invariant subspace. So let me take M to be a star algebra. So M a star algebra.
That is M prime or M?
M
The
prime.
first one, M prime.
M prime. Say that it is invariant for everything. It is invariant for M, but the same as saying that the orthonormal projection is in M prime.
That should be M. There's a prime there.
Which?
The statement
Oh.
1.
Statement no. Means the space is
So you
reducing.
say-
It means the space is reducing for M. I mean that B prime
Yeah,
commute with every element of
I'm just coming to your way. I want to make some noises which will address all these things you're saying. So I'm trying to say that any operator on a direct sum can be naturally thought of as an operator matrix, where an element of the direct sum you can think of as a vector of the form x1, x2, x7. Again, I'm writing bad habits. Yeah, I'm writing. I have written x and xij. Can you go to the new page? Start the new slate. So I want to say that x in p of h1 is on h2. And it can be identified with the matrix x1, 1, x1, 2, x2, 1, x2, 2. With xij, p of hj, hij. Where the thinking is that you represent operators in h1 direct sum h2. If you think of an x in h1 direct sum h2, you think of as column vector x1 x2, with the xi is coming from hi.
X.
Xi. Take a vector in h1 direct sum h2, think of it as having empty from h1 and h2. Then they say that if you want to see what xi is, it is given by just taking the matrix xij and multiplying it by the column vector xij. In the only sense that makes. If you multiply this by xi1 xi2, then you have x11 xi1 plus x12 xi2. The thing operators work in the right spaces to the right spaces. And you will see that this is exactly what you do. Okay. So now coming back to this thing. So let me observe the following thing. Suppose I take one operator x in each, p of each. They decompose with respect to each one, h direct sum h per. So h naught direct sum h naught per. Or let me say, suppose h1 is the subspace of h, and h2 is equal to h1 per. You write the right thing of x as an operator matrix. What does it mean to say that h2 equal to h1 per? What does it mean to say that, so this is going to be matrix, to say that x maps each one into itself. What does that mean? If you think of it as a matrix, what does it mean to say that map? It is like in two-dimensional space. What does it mean to say that it maps the first quadrant space into itself? That means if you look at the matrix, the 2, 1 entry should be 0. This amounts to saying that x21 is 0. So to say that one operator given one subspace invariant means that when you take the natural decomposition of the Hilbert space along that subspace and its complement, that one that corner should be 0. So now the proof of that proposition is more or less straightforward. So to say that X, everything in M lives, it's not invariant. Means that for everything in M you take its matrix decomposition, and the decomposition is not delta, is not per. What you're saying is that all of them will have the 2-1 entry as being 0. But M is supposed to be closed under adjoints. So if everybody has in M has 2-1 entry 0, if you apply it to the adjoint or something in M, you will find that the 1-2 entries will also be 0. So to say that something that this H0 is invariant for everything in M, which is a star algebra, will imply that everything will have a diagonal matrix. That means they will commute with that projection, which is like the matrix 1, 0, 1, 0, 0, 0. In the matrix formulation, the matrix of this projection is just identity on H1, 0, 0, 0. Okay. Okay. So after having made choose. Okay. So I want to use this fact to say that subspace is invariant for a star algebra is equivalent to saying that its associated position belongs to the combinator. So now let me prove this theory should be called density theory. This is really it says the same thing as what the double coordinate theorem says, but in a different case. So the statement is that if A is a maybe I need to do yeah. Star algebra with containing 1. Unit to star. Then I want to say that A is any star algebra is dense in the strong operator topology in its double commutator. And so this is another way of saying the double commutator theorem. If I know that it is already everything, if I know that it is equal to a double commutator, or if I know that it is already strongly closed, there is the same thing. That is what this will imply. So I will prove this, and the other thing is really the consequence of this fact. So then we are going to exercise and understand, getting the grips with this, with these different topologies, and what it means to say that something is dense and something. Okay. So by definition of the strong operator topology, so I need to show that if A double prime is A double prime and omega is an associate open neighborhood A double prime. I want to show that omega contains an element in A, and that is what this means. Right? by so I want to show that okay. So by definition of the SOT strong operator topology on DFA, what this amounts to saying is that if so, what does a typical SOT open neighborhood of a point look like? So you must go to the definition of the topology. To require so for it to be for every xi you want x to xi, the map x squared to xi to be continuous. So a sub-basic open neighborhood will be given specified by choosing one vector and one epsilon, and looking at all those things which are within epsilon of that. So I'm saying that I'm just unraveling the definition of this topology. So I don't want to spend too much time on the points. What this means is that for all xi1, xin, H. So a typical, if I define omega as all those x such that norm of x minus a taking on psi is psi I equal to so a typical basic open neighborhood of the point A double prime will look like looking at all those operators x, which when at this finite number of many vectors xi1, xi differ by less than epsilon from A double prime. Is this we'll go through. So, if you're not convinced of this, we'll maybe talk about it in the afternoon or something. So I tell you that what you need to check is this. If I define omega to be this set, there is omega defined by specifying finite collection of vectors and an epsilon, and then wanting to look at all those operators which are within epsilon from A double prime when you act on any one of these parity vectors. That is the set omega. And then I want to say that this omega contains something in A. To see this, let me first do the baby case of n equals 1. So for that omega, what I have to choose xi1, xi2, xn, and I wanted to find something which is so what I need is to find, so to prove that there exists A such that norm of A minus A double prime right is different. This is what I need. And so what one does is one. So take take the closed areas of space spanned by ASI, by ASI, we have 4 B. All things will form little a acting on psi, little a. So this is by definition some closed subspace of Hilbert space. So let me call this H naught. And let the P prime be P H naught. Okay, so I think what am I given? I'm given that. So I first observe that H naught is A state. Because A is an algebra. If I act on any, if I take something of the form B is I in the dense collection, and then if I act on it by A, then I just get AB acting on Z. Because A is an algebra, it is clear that ASI is invariant under left quantification by anything in A. And because elements of A are continuous operators, that is true of also the closure. So any operator in cap A must leave H0 invariant. So if H0 is A invariant, that will mean that by what that Lemma said, it will mean that P prime is in A prime. Because A is a star algebra, that's what we were assumed. But then, and clearly, I've assumed that A had identity. So that means that Xi is in H0. Xi is in H0, and if I look at A double prime now, by definition it must commute with P prime. So if it commutes with this projection, what does it mean? If you look at that operator, as I already remarked, it will have to be diagonal if it commutes with the projection. Because this and it adjoint commute with the projection. So A double prime must leave H naught invariant. Is that clear? A double prime commutes with P prime. And P prime is the projection, P prime is this matrix. Who are the operators which commute with P prime? They are precisely the operators which are diagonal. And if we take any diagonal operator, then they clearly leave the first subspace invariant. Or the second, which is the orthogonal component. So if A double prime commutes with P prime, it must leave H naught invariant. Therefore, that means A double prime beside must be in H naught. Because I is in H naught. But H naught is by definition the closure of AZ. AZ is a linear space. See, A is an algebra, so it is closed under linear combinations. So ASI is already a vector space, so this H naught is nothing but the closure of AZ. So that means that A, so that, or let me say A and A, so that A and Z converges to A double prime Z. So in particular, one of them will be within epsilon. I've given the A double prime, the psi and the epsilon, I've been able to find an A, which does. Okay, now to complete this proof, see, I took only one simple case of taking one vector. I must take n vectors and try to do the same thing. And so this very clever little trick of Orthonormal. She notices the following fact. See, this is also stated in some excerpts. This is out as exercise. So, okay. So if you look at these notes, so I don't have to write everything down. If you look at exercise 1.9, there is so for any of you take a representation of V of H on V of H to the n. Take a direction of n copies of H, and for every operator A and H, I think of A acting on the direct sum by just A direct sum itself n times. So that phi is clearly a representation of a homomorphism, star preserving whatever.
I didn't see that.
So the point to observe is that if you take, if I write A n for things of the form A repeated n times on the diagonal, A in A, then what is to be observed? So this A to the n is a subalgebra of V of H to the n. It is as much a subalgebra as A was. If I call this as something died, is it? Okay, actually the tensor notation is, maybe the physicists will also be happy with it. If I write for an A and B of H, if I write A tensor 1 and as this matrix A, and if I write A in we all such things A and A. Then I'm observing the repeating A going to A tensor 1 is clearly a star preserving, product preserving mapping. So A n is a star algebra, just as A was. And if you take A n commutant, so there's just idiot multiplication you have to do. Take a matrix Bij and see when it commutes with this diagonal matrix A. So you can see that there is exactly things of the form. It is the manifesto, we just look at the thing. If you multiply a diagonal matrix A by matrix Bij, then you get A Bij at the entry. If you multiply it the other way, then you get Bij. To say that the commute Bij commute means that all the entries must come from the commutant. So the commutant of An is this, from which it follows then also that An double prime equal to A double prime N. So what this little device does for us is to say that if I want to say that, so I apply the n equals 1 case of what has already been proved, but to this a n rather than a, to reduce that if I look at a double prime times 1n. So that is something in here. And so if I take one vector in the underlying Hilbert space, which I think of as I1 by n, this is a vector in Hn, and if I give myself an epsilon, what the previous case would say that this was in this here. So the previous case will say that there is something in this An which is an An. So it will say that you can there is an An, that there is An minus A double prime n on this vector, right? This is an epsilon. Yeah.
You have written Aij prime. So that should that be Ai prime, because like it is only diagonal terms.
No. The commutant may not be diagonal.
Okay. It can be anything.
Can be anything. You take. See, when I say I want the commutant of this collection, what do I mean? I want all those operators which commute with everything here. That operator need not be diagonal. So I look at all possible matrices which commute with everybody like this. And so those should look like something with all the entries coming from the commutant of this algebra. That's what this answer is. Good. Okay, let me just take two more minutes to say something that we will need next time. Namely, if you take, see, I did an n-fold version, an n-dimensional amplification of the operator. That is, I took a representation by n from V of h to V of h. So this is a certain representation, we meaning a star homomorphism of algebra, and this is what one used when n was finite. So one can do this for any n. I can take an infinite direction. Each n I think of as an infinite direction of infinity many copies of it, and I just look at pi infinity as the thing which sends A to the diagonal matrix, the big infinite matrix with A's on the diagonal. If you do that, then the noise observed is that the pi infinity from V of h to its image this is bijection clearly. And by exactly the noises that I made, that if I take an A, then if I take A infinity double prime, that means I have an A double prime infinity. So, in fact, this is going to be equal to its own double prime. That is by earlier statement that A. The statement that A n double prime is A double prime n. That same thing happens even when n is infinite. The argument is all just algebra. If you apply it to the algebra, that means that this is a one-dimensional algebra. So what that will say is that this so what this will say is that on V of H infinity, I have the strong operator topology, weak operator topology, whatever. Now this has been identified through this by infinity with something in V of H infinity. So if I transport the topology in V of H infinity back to V of H, if you see what that says exactly, so this will, so under this by infinity, so I can pull back these topologies, by infinity star. That is, I'm being a little sloppy here. So what I'm saying is that the image of this is certain subalgebra over here that has certain topologies that it inherits a subsquare topology for these coming from here. If I pull those topologies back to the B of H, there pi infinity x alpha must converge to pi infinity x strongly. That means if I act this on any vector in H infinity, which looks like an infinite sequence, converge to this in this sigma is 4. Sigma usually refers to any countable operation. If you just unravel the definition, this just what do vectors in H infinity look like? They are given by sequences of vectors which are norm square sum of them. Summation norm Cn squared must be finite. So this corresponds to saying that summation norm x alpha minus x In squared converges to 0.
Finite. Whenever norms n squared.
Finite. Whenever norm n squared is finite, you want this to go. And what is important for us next time we'll see the sigma weak topology, which is required by saying that summation over n x alpha minus x In eta n converges to 0. Whenever summation norm n squared and norm eta n squared, then is the sigma V topology, which has a very important role. In fact, what we the double Cometron theorem that I stated earlier can be strengthened to say that there's actually the same proof as I gave for the mononomial density theorem will say that if A is a star unit of star algebra, it is actually sigma weakly dense or sigma strongly dense. That proof will show that it is sigma strongly dense in its strong closure. It is double Cometron. The same proof will show that I had those two kinds of big closed in two topologies is equivalent to the double Cometron theorem. Double Cometron statement is true. So either of those topological conditions can also be replaced by these sigma strong and sigma weak with exactly the same reason. So I've gone overboard already. So should one save the not anything? Huh? Save the type for the machine.